Welcome to today's lesson. Today we're going to be talking about transformations of trig functions. Vertical translations of trigonometric functions. If I have f of x equals sine x plus c, if the c is positive, then the whole graph will be shifted up from black to red. If I have f of x equals cosine x plus c and my c is negative, then I shift the whole graph down. Here's another example of shifting the graph down. Tangent x plus c, where c is negative, I will shift my whole graph down. My center line goes from here to up when c is positive, from here to down when c is negative, from here to down when c is negative. We can translate trig functions horizontally as well as vertically, but the key here is to remember it's just the opposite of what you think. If my original sine function is in black, sine x plus some angle alpha is going to push me to the left, and that will be my red curve here. I've been taking the black and I've pushed it to the left. Sine y equals sine x minus alpha pushes me to the right. So if my original was the black curve, pushed to the right would be this blue one with the negative sign, just the opposite of what you would expect. The same is true for horizontal translations of the cosine curve. Cosine x plus alpha says push me this way. My original black curve is here for cosine. Push to the left as it's a positive angle there. So that would be my red cosine x plus alpha. Cosine x minus alpha says push me to the right. So if my original curve was here in black, x minus alpha would be pushed to the right, and that would be my blue curve. And finally, we see the same for horizontal translations of tangent. X plus alpha says push it to the left. That's the one I've drawn here. Here's my original in black. X plus alpha will push me to the left. Conversely, x minus alpha would push me to the right. I thought it would get confusing if I drew another blue curve, but a blue would drag me to the right if it was minus alpha. We can now talk about dilations of trigonometric functions. There's two things you need to know. One is that the dilations do not affect the shape of the graph. The general shape will stay the same. And that the dilations are pulling us along the y-axis, away from the x-axis, parallel to the y-axis. Let's take a look at y equals sine x in black. Well, we have what we call an amplitude of 1. It's this distance between our center line and the highest point, and our center line and the lowest point is 1. We go up to a height of 1 and down to a depth of negative 1. If I multiply by 2 out in front, I'm going to double my high. So now my amplitude is 2. And my depth here is also 2, or negative 2. When we dilate a cosine function, we have the same sort of situation. We go from cosine x, which is this black curve that has an amplitude here of 1, a minimum of 1, and a maximum of 1. And when we multiply by a constant out in front, this becomes our amplitude. Our highest value is 2 away from our center line, and now our lowest value is 2 away from our center line in the negative direction. Although we really can't talk about amplitudes with the tangent function, you can see that the green function y equals 2 tangent is stretched away from the x-axis parallel to the y-axis, because all of our values, both negative and positive, are doubled. Let's consider dilations of the parent function parallel to the x-axis. My parent function is y equals sine x, or f of x equals sine x. If I multiply by b inside the parentheses, no longer outside here, but inside, I'm now changing the period. The period is the amount of space or time or angle we need to complete one full cycle. For the sine, it might look like that, up to down. In our parent function, y equals sine x, here in black, we see our period is 2 pi. Well, really, our period is 2 pi divided by b. You need to memorize this, that period is 2 pi over b. So, y equals sine x transformed into y equals 2 sine 2x. Our b is 2. So we can find our period as 2 pi over b would be 2 pi over 2, which we simplify to pi. Well, what does that result on our graph? We've scrunched our graph because now we have to get one full up and down cycle in from 0 to pi. From 0 to pi, I go up and down. From pi to 2 pi, I go up and down again. Notice b is also representative of the number of cycles from 0 to 2 pi. In this example, b was 2, and we had one full cycle and then another full cycle. So b tells me the number of full cycles from 0 to 2 pi. And I need to know that the period, or the amount of radians I need for one full cycle, is equal to 2 pi over b. That's unique to the sine curve. When we're talking about dilations parallel to the x-axis, the cosine is very similar to the sine. If I have f of x equals cosine bx, my period, the amount of space I need to make one full cycle, has been altered. Again, the period is going to be 2 pi over b. For both cosine and sine, we see this 2 pi over b relationship. For example, if y equals cosine x, I could translate that into y equals cosine 2x, where my period, if my b is 2, then my period will be 2 pi over b, 2 pi over 2, which is pi. In other words, I have to fit, if this is my parent function, y equals cosine x, I have to fit one full cycle in between 0 and pi, and then another full cycle in between 0 and pi. I saw my b was 2, and b again tells us, not only it can be used to find out the period with 2 pi over b, it also tells us the number of cycles between 0 and 2 pi. We see we had 2 cycles between 0 and 2 pi, and our b here was 2. Finally, when we're talking about dilations parallel to the x-axis, we consider y equals tangent bx. Well, tangent is different from sine and cosine. Tangent has b cycles in not 2 pi, but pi radians. And our period is not 2 pi over b, but pi over b. Notice, instead of 2 pi, it's pi. Instead of 2 pi over b, it's just pi over b. This is the one that I start with here, though. We have one cycle between negative pi over 2b and pi over 2b. This is my most important one to start with. For example, if y equals tangent 2x, where our b is 2, we know that our period will be pi over b, which is pi over 2. So we have one full cycle in just 90 degrees, or pi over 2. And we're going to have one cycle between negative pi over 2b and pi over 2b. So that's negative pi over 2 times 2, because my b here is 2, and positive pi over 2 times b, which is 2. So I know from negative pi over 4 to pi over 4, I'm going to have one cycle. That's where I start. Negative pi over 4 to pi over 4, I have one cycle. And I found out my period, which was pi over b, was pi over 2. So I went over 90 degrees, or pi over 2, to find one full cycle. We can now talk about reflections of trig functions over the x-axis. Here is our x-axis. We're going to flip this black curve, y equals sine x. Notice amplitude of 1, period 2 pi. We're going to flip that over the x-axis. So our positive values over pi over 2 up 1 becomes over pi over 2 down 1. And over 3 pi over 2 down 1 becomes over 3 pi over 2 up 1. So our curve is a reflection across the x-axis. It goes down and then up. All of our y values have been changed from positive to negative and from negative to positive, with this negative side in front of the sine x. Similarly, we can reflect cosine x, which is in black here, down and up with a period of 2 pi and amplitude 1. We can reflect that over the x-axis by putting a negative out in front. So my positive 1 goes to negative 1. And my positive, my positive 1 goes to negative 1, and my negative 1 goes to positive 1. Our graph with a negative out in front reflected over the x-axis goes from down to up and back down again. Finally, we have our reflection of trig functions over the x-axis using y equals tangent x. In black we have from negative pi over 2 to pi over 2 for our parent function, and then pi over 2 to 3 pi over 2 for our parent function. Well, if we put a negative sign out in front, that's going to change all of our y values, and we're going to reflect this over the x-axis. So we get our curve sort of going down like this. Notice the period here is pi. We can now talk about reflections of trig functions over the y-axis. If the black curve from 0 to 2 pi, if I restrict my domain of this black curve from 0 to 2 pi, is y equals sine x. There's our parent function. Well, if I want to graph y equals sine of negative x, notice the negative is now inside the parentheses associated with the x, that's going to flip our graph around. Any x I put in, I'm going to take the opposite of that x value and I'll get the same y value. Meaning that this point will go to there, and this point will go to there, and this point will go to negative 2 pi. A negative inside the parentheses flips all of my values across the y-axis. Similarly, for the cosine curve, in black, from 0 to 2 pi, I drew y equals cosine x. If I want to graph y equals cosine of negative x, that's going to flip me over this y-axis here. So that this point here becomes this point here at negative 2 pi corresponding to 2 pi. And this point here at pi over 2 becomes negative pi over 2 here. And last but not least, if we talk about reflecting the tangent function over the y-axis, the original black curve, if I'm thinking about the x or the domain going from 0 to 3 pi over 2, looks like that. And if I'm graphing y equals tangent of negative x, I'm going to consider that to be flipped over or reflected over the y-axis. So we have a mirror image. That point becomes that point. That point becomes that point. That point becomes that point. Let's put it all together. Combine transformations. If f of x equals a sine b, x plus c, plus d, notice it's outside parentheses, or f of x equals a cosine b, parentheses x plus c, all in parentheses, plus d, we know our amplitude, or the distance from our midline to the highest or lowest point, is the absolute value of our a term. The period for both sine and cosine is 2 pi over b. Horizontal translation is c. Notice we have plus c and plus c. If c is positive, it's the opposite of what you're thinking. We're going left. If c is negative, then we're going right. Vertical translation, it's whatever d is. If d is positive, we go up, and if d is negative, we go down. Notice c is the tricky one. It's opposite of what you would think. I realize that this is a small, picky point, but it's important to make. Be careful with b. First, we have to express all of our functions if we're talking about cosine or sine, but in this case we're talking cosine, as a cosine parentheses b times the quantity x plus c plus d. If you're given f of x equals this, you may be tempted to say, well, your b is 3, and your horizontal translation is pi over 2 this way. However, we first have to express it exactly like this, so we have to factor out that 3. When I factor out that 3, I can say 3 times x does give me 3x, and 3 times pi over 6 really does give me 3 pi over 6, which is pi over 2. So I haven't changed anything when I do this factoring, but now you can see actually our horizontal translation is pi over 6 this way, not pi over 2. Here is the problem when you don't have this factored out. The note is, be careful with b and factor out the b. Last but not least, we can talk about combined transformations to the trig function tangent. If f of x equals a tangent b times the quantity x plus c, all in parentheses, plus d, we have no amplitude. Remember, the tangent function had asymptotes and our y values reached positive infinity and negative infinity. So amplitude is not appropriate. Period, instead of being 2 pi over b, as we saw in sine and cosine, our period now is pi over b. And remember, we started here, always, one cycle from negative pi over 2b to pi over 2b. Our horizontal and vertical translations are the same as we saw in the sine and cosine functions, where if c, in the horizontal direction, is positive, we're going to the left, and if c is negative, we're going to the right. Vertical translations of d units is what you would expect. If d is positive, we go up, and if d is negative, we go down.